This video is the demonstration of snap fit simulation using ANSYS Workbench. In this case, there are two snaps. The first snap is the top snap, which is fixed in all degrees of freedom at this location. The second snap is the bottom snap, which is given a displacement constraint along the negative y-axis so as to ensure the snap fit. A key observation in this animation is you can find there is a localized mesh refinement around the snap fitment. This is to ease the detection of contact, and in this area the results are of interest, whereas the other region of the snap is meshed with a larger element size in comparison to the elements at the contacting region. This is done generally to reduce the computation time. This problem basically is a 3D model problem. This 3D problem is converted into a simple 2D problem to reduce the computation time and to simplify the problem without affecting the results, which means there is no compromise on the results which are obtained. Here is a complete demonstration of the snap fit simulation. Let us begin with the tutorial. Create a new static structural analysis file. Rename the file as snap simulation. Enter. Under Properties, change the analysis type to 2D. Right-click on the geometry and import the snap model. Now you can observe a tick mark, which is the geometry is loaded into the design modeler. Right-click on the geometry, pick on Edit. This will open the design modeler. Ensure the units for the ANSYS Workbench. In this case, it is millimeters. Pick on OK. You can find the geometry is now attached to the design modeler. You can observe an update symbol, which means the geometry needs update. Before we could update, let us cross-check the details of the import. The solid bodies need to be imported. Yes. Surface bodies need not have to be imported. No. Line bodies need not have to be imported. Make sure that Advanced Geometry Options analysis type is set to 3D, because we are importing a 3D model and converting it to a 2D analysis. Now pick on Generate at the top left corner. This will import the geometry into the design modeler. Observe a message in the bottom message window, Generating feature. The snap model is now imported into the design modeler. Carefully observe, this 3D model is having a constant cross section, which means the same cross sections across any plane along the length. Such problems can be simplified to 2D problems. Let us extract the mid surface or the middle surface of this snap assembly. Pick on Tools. Pick on mid or middle surface. Select the first face and the second face of the snap 1. Pick on Apply. Pick on Generate. The mid surface for the first snap is now extracted. Similarly, extract the mid surface for the second snap. Tools, Mid surface or Middle surface. Select the first surface and the second surface. Pick on Apply. Pick on Generate. Mid surface of both the snaps are now extracted. For ease of mesh refinement, let us split the surface around the snap area. Set the view orientation to front view. Let us try to trim. Pick on Sketch or New Sketch. Under Sketching, use the rectangle command from the Draw toolbar. Draw the rectangle. Once the rectangle is drawn, pick on Modeling. Pick on the tools. Pick on Face Split. Select the face. Pick on Apply. Under the tool geometry, ensure that the edge is selected from Selection filter. Pick on this edge. Pick on Apply. Now pick on Generate. The top snap is now split by this line. Similarly, pick on Tools. Pick on Face Split. Under the target face, pick on the bottom snap. Pick on Apply. Under the tool geometry, ensure that the edge is selected under Selection filter. Pick on the bottom line. Apply. Pick on Generate. The faces are now split. These two snaps now can be taken for the analysis. Switch off the sketching plane. Now, go back to the project page. Double-click or right-click on the model and pick on Edit. This will start the mechanical window in which the design modeler geometry will be imported. The Attach Status window is now open. The geometry is imported. Reset the window layout from View, Windows. Reset Layout. The window is now reset. Pick on Graphics so that the geometry can be seen. Let us define the connections, meshing, analysis settings, loads, boundary conditions, and desired results. First, let us begin with defining the mesh. Right-click on the mesh, pick on Insert, pick on Sizing. Select these two faces, pick on Apply. Enter the element size as 0.2 because we want to have the mesh refinement in this snap contacting region. Let us define the contacts. Under the contact, it can be found there exists one contacting region. The top snap is highlighted in the red edge and the bottom snap in the blue edge. Blue represents a target edge, red represents a contacting edge. Let us redefine these edges to include more number of curves in the contact. Pick on the contact edges and extend the edges to these all edges. Once the edge picking is completed, pick on Apply. Similarly, pick on the target edge. Select the target edges. Pick on Apply after the edge selection is complete. Let us convert this bonded contact into frictional contact with a desired properties. Make sure the type is frictional. Enter the coefficient of friction as 0.05. This low coefficient of friction is to ensure the smooth contacting. Keep the behavior of the contact as symmetric. Under the formulation, make it as pure penalty. Under the interface treatment, make it as add offset no ramping. Under the detection method, make it as node normal to target. Normal stiffness factor, keep it as manual and enter the manual contact stiffness as 0.1. Update the stiffness for each iteration. Enter the pinball region as a manual radius or 0.2. Once the contact definition is complete, pick on any of the body or pick on the mesh first, pick on any of the body, right click, generate mesh on the selected bodies. This will generate the mesh. Similarly, pick on the other body, right click, pick on generate mesh on the selected bodies. Once the meshing definition is complete, let us apply the loads and boundary conditions. In this case, let us fix the bottom snap and let us displace the top snap. Right click on the static structural. Insert, pick on fixed support. Ensure that the edge is selected under the selection filter. Pick on the edge, pick on Apply. The top edge or the root edge of the bottom snap is now fixed. Right click on the static structural, pick on Insert, pick on Displacement Constraint. Apply the displacement constraint on the edge of top snap and pick on Apply to ensure the geometry selection. With respect to the global coordinate system, the top snap has to displace in the y direction. for an amount of -3, and it should not displace in x direction. Pick on a constant value of 0. Now, the boundary condition is defined. Let us proceed for the analysis settings. Analysis settings is very important for any analysis. We are going to do only one step analysis. Hence, the number of steps is 1 and the current step number also is 1. This analysis will end at a time duration of 1 second. Under the automatic time stepping, pick on, which means we are going to control the movement of the snap. This movement should be always smooth and gradual so as to ensure the contact at each point of the snap fit. Enter the initial substeps as 1000. Enter the minimum steps as 20. Enter the maximum steps as 1000 again. Increased substep values will increase the computation time. Remember, under the solver type, make it as direct. Under the weak springs, switch off. Under the last deflection, switch on. Once the necessary analysis settings are done, insert the desired results. Right-click, insert, pick on stress, pick on von Mises stress. Right-click on the solution, pick on insert, pick on deformation, pick on total deformation. Once the results are inserted, let us proceed with the solution. Right-click on the solution, solve. Under the solution information, it can be observed the solution output for force convergence. It can be observed the solution is currently at 0.3, 0.4, 0.5. This will take a few minutes of time to complete the solution. Once the solution is completed for a time duration of 1 second, it is a time to proceed to retrieve the results. Pick on equivalent stress. Let us animate the results for predicting the accurate behavior. Enter the number of frames as 100 and time of duration as 10 seconds. This is for the animation purpose only. Hide all the windows. Let us observe the predicted behavior. Pick on graph. Pick on animate button. This will take a few seconds of time as number of frames is more. Switch on the elements. Pick on the graph and animate it again. This is how the snap is going to behave. Thank you for watching this video. If you like this video, click on the like button. For more videos, please click on subscribe.